All right, we're going to take a quick look at solving quadratic equations, but in a way that has nothing at all to do, well, I guess not nothing at all, but a way that has nothing to do with the quadratic formula, or even completing the square, which is really the process that we could use if we took that, standard form ax squared plus bx plus c. If we completed the square on that, you get the quadratic formula. So we're going to look at a process that doesn't involve any of that at all. And this is something I've recently discovered. Wish I would have come across this a long time ago. So I want to share it with you now. So we're going to make a couple of assumptions here, or just kind of set the stage for where we're moving. So we'll give an axis, a coordinate plane here. We'll give a little quadratic function, and then I'm going to label this parabola with a couple points. So here's our roots. We'll call them R and S. And then a couple of things that you may not have thought about before that we're going to use is I'm going to call M the midpoint. So like the midpoint between our roots, halfway between them. Guess this is also the the x coordinate of that midpoint would be equivalent to the x coordinate of the vertex as well, would be the same as that. And then also one other piece that I want to point out is then that distance between the midpoint and the root. So just establishing a couple things there. And then just starting from here, very algebraically, I want to just represent algebraically, I guess I should say, what this function would look like just in terms of Rs. So I know I could write that as x minus r times x minus s. And then I'll go ahead and multiply these out. So x squared minus sx minus rx plus rs. And then we're going to do a little cleanup with these two terms here. I can factor out a negative x, s plus r. And then I'm going to move the x over here, minus, and then switch these terms around, r and s, just to keep them kind of left to right like we had initially. All right, so here we go. Now, if I wanted to compare this to, let's say, ax squared plus bx plus c, what I'm kind of establishing and setting up here is that if we are given a quadratic equation in this form, all right, if a is equal to 1, so I guess I should go ahead and establish that we're just talking about context where a is equal to 1. If we're working with something where it's not equal to 1, we can just scale up or down and make it equal to 1. But if a is equal to 1, okay, b is going to be equal to the opposite of the sum of the roots, and c is going to be equal to the product of the roots. So you can just kind of see by direct substitution there, those two things. And this is something you might have already intuitively have known. If I were to give you a quadratic equation like this, x squared plus 8x plus, let's say 16, a pretty common way to factor this, something that I think a lot of people would look for, is kind of this thinking here. I know that when I factor this out, first of all, because x is 1, or a is 1, it's just going to be x and x, that I'm looking for two factors of 16 that I can add together to get 8. And in this case, that is 4 and 4. So then we could solve x plus 4 equals 0 and x equals negative 4. Now, that process and what we kind of looked for is what is kind of generalized by this statement here. All right, so just kind of establishing some things that we need to know, some things moving forward for the rest of this thinking. That in terms of the roots, we can think kind of back and forth between the coefficient of this linear term and the constant. Both, we can think of those both in terms of the roots right here. So this is kind of an important step. This is some understanding that we're going to work from. All right, now, building from that understanding, if m is the midpoint. If m is the midpoint of the roots of r and s, then something that has to be true, m has to be equal to the average of the roots, right? On a number line, the midpoint distance is just the average of the other two distances. And then to go one step further, right, we just talked about how b is equal to the opposite of that sum. Then that must mean, all right, that must mean that m is also equal to the opposite of b over 2. So just given any quadratic equation, let's say x squared plus 6x minus 11, just given any quadratic equation, if a is 1, all I have to know is b in order to know what the midpoint is, between the two roots. So I may not know the roots, but I do know that for this equation, the midpoint of the roots would be -3. It's the opposite of half of that. The opposite of 6 is -6, and half of -6 is -3. Now, knowing the midpoint, all I now need to know in order to find the roots is the distance that each root is, which is the same distance, just plus one way minus the other way, that distance, okay? So in order to find that distance, we're going to start from a couple other assumptions, some things that we already know. So if m plus d is equal to s, okay, and we see that visually here. M, if we go this, some distance d, and we get to that root, and m minus d is equal to r. So we just go the other way and we get to r. And if it's the midpoint, that's true, okay? Then we could take those two, m plus d and m minus d, multiply those together, and we would get SR. And just to keep it consistent, I'm going to commutative property here, flip that around and say RS. Now, we could do a little bit of simplifying here, a little bit of multiplication. I'm going to skip some steps in between. If you want to pause this and work it out for yourself, feel free to do. But if we work down, we would end up with m squared minus d squared equals RS. Now, I'm going to substitute one more time because we also know that RS is the same thing as C. And that's important to think of that as C because that's an amount, that's a value, something we'll have just by looking at the equation itself. So I'm going to say m squared minus d squared equals C. Now, again, I'm going to do some simplifying, rewriting to isolate this for D, because if you remember just a minute ago, that's what we talked about we really needed. What we need to know, if we know the midpoint to find the roots, is that distance going each direction. If you want to pause and do that for yourself, feel free, but I'm just going to go ahead and clean that up and write out here. D is equal to the square root of m squared minus C. So what that tells me, looking right here at this sort of formula, we could think of it like a formula, is that if we know C, which we would know C given an equation, I'll start with that same one, that x squared plus 6x minus 11. We would know C, that's negative 11, right? So minus negative 11. And if we know m squared, which finding m isn't too difficult. Remember, m was just the opposite of b divided by 2. So negative 6 divided by 2 is negative 3. And we find the square root of that, we will get d. We will get that. Distance. So this will give us 9 plus 11 is 20. And so the square root of 20 is how far away each of those points are from that midpoint. And really here, we now have enough information, right? Or I guess I could say m equals -6 divided by 2, which is just -3. So now we have all the information we need to find those roots, right? Remember, think back, if my roots are here and here, R and S. If I know that midpoint is at -3, and I guess obviously this is not at -3 because of my x-axis is in the wrong place. And then we know how far we got to go to the right and to the left, which is just plus the square root of 20 and minus the square root of 20. Then we will have the roots. So here we could say or represent our roots, right? X equals -3 plus or minus the square root of 20. Or just in general, we could say x equals m plus or minus d.